Part 1, I talked about the importance of parameterizing curves in multivariable calculus, especially when we get to something called line integrals later on in the quarter. So I have a couple more examples of this. The first of which is another circle. This time I have a circle of radius 3 with a given center, and I specifically want a counterclockwise parameterization of that circle beginning at some point. So what do? Let me draw a picture here to get us situated. Here's our circle. The center is the point -1, 1. And we're looking for a parameterization where we start at the point -4, 1. In this case, that would be the point over here. And I want to travel counterclockwise, which would be this direction. As before, my starting point here is going to be the standard parameterization of the unit circle. In particular, the usual way that we parameterize the unit circle is by calling x cosine of t and y sine of t. Now with this parameterization, this gives us something where we specifically start at the right-hand endpoint and travel counterclockwise. So when t is 0, cosine is 1 and sine is 0, so I start at the point 1, 0 over here. And when t is pi over 2, I'm at the point 0, 1, which is up here. So what I'm going to do is I'm going to think about this parameterization and figure out how I can tinker with it so that it looks more like this. The first thing that we need to think about is, what if I wanted to take just this unit circle parameterization and start it over here at the point -1, 0. That would be analogous to what we want to do over here. So let me write that down. For the parameterization that we're looking for, we want t equals 0 to spit out the point -1, 0. So I look at this and I think, well, when t is 0, sine of 0 is still 0. So a decent guess is that, oh, maybe I just want to keep the y component as sine. Now, to start at -1, since cosine of 0 is 1, if I put a negative sign in front of the cosine, then I would start at the point -1, 0. So then r of 0 is exactly this point that we want. The problem is that I don't actually think that the direction is correct here, because when t is pi over 2, what point are we at? Well, cosine of pi over 2 is 0, so I'm at the point 0. Sine of pi over 2 is 1. So with this parameterization, when time is pi over 2, we're up here, which means we're not traveling in the correct direction. In order to fix that, to get to the point 0, -1 after pi over 2 time units, I could put a negative sign in front of the sine function. If we do this, then after pi over 2 units, we are at the point 0, -1, which is down here, which means we're traveling in the correct direction. Okay, and so this parameterization right here parameterizes the unit circle, which is not what we want, but the qualitative behavior is the same. So what we can do is we can just take this thing and squish it around a little bit so that it turns into the circle that we're actually looking for. Okay, in particular, one thing that we want to do is we want to adjust the center. To adjust the center of a circle, I can just add the relevant units to each component of the parameterization. So in particular, my x component is going to look like -1 plus some stuff, and the y component is going to look like 1 plus some stuff. Doing this effectively just takes this picture that we're starting with over here, shifts it to the left by 1, and then up by 1 as well. Now the x component we decided we want to look like negative cosine of t, but I want the radius to be 3. I can adjust the radius by scaling the cosine by 3. So negative 1 minus 3 cosine t would be the correct adjustment of the x component. Likewise, 1 minus 3 sine of t would be the correct adjustment for the y component. And there you go, and we can check that this in fact does what we want. R of 0 here is going to be the point. Well, cosine of 0 is 1, so this is negative 1 minus 3, which is negative 4. And then sine of 0 is 0, so this is 1. So we do start at the correct point, and then we can check that the direction is correct by looking at our position after pi over 2 seconds, for example. When t is pi over 2, cosine of t is 0, so this will be the point negative 1. And then sine of pi over 2 is 1, so this will be 1 minus 3, which I think is negative 2, which is in fact the point at the bottom of the circle. The circle has radius 3, so if you start at the point negative 1, 1 and go down 3, you land at the point negative 1, negative 2. So that checks out, and this is exactly what we want. And there you go, we're done. Next up is another problem where we parameterize the curve of intersection of two surfaces. This time I have a surface given by y squared plus z squared equals 3, and a surface given by z squared plus x minus 2y equals 1. So I'm going to try to draw a picture so that we can think about this geometrically, but as usual, a good skill to develop in this class is going to be just trusting the equations and not getting too caught up in the visualization. Drawing pictures is great, being able to visualize the geometry is great, but a lot of times it's really hard and sometimes it's not necessary. So trusting the equations is a good lesson to take away from this. Here's what I mean by that. If I gave us the equation y squared plus z squared equals 3, that should make you feel like a circle. And that's in fact what it defines in the yz plane. This is a circle of radius square root of 3. Now, this represents a surface. That surface is going to be that circle in the yz plane extended in the x direction with no restriction. Because there's no x in the equation, there are no restrictions on x. So this surface up here is going to be some cylinder along the x-axis. Let me try to draw that. Okay, so here's this cylinder in blue. Like I said, this represents y squared plus z squared equals 3. You can think about these vertical cross sections, if I chop through like this, as being the yz plane. And when you chop through like this, you get the circle y squared plus z squared equals 3. Now the second surface is a little weirder looking, but what I identify is that I can solve for x as a function of y and z. Let me write that down. The second surface I can rewrite as x equals, let's see, move the 2y over, this will be 1 plus 2y minus z squared. Again, I don't really know what this looks like. We could figure it out if we had to, but the important point is that x is a function of y and z. The reason why this is important is because what we're going to do is we're going to use the blue surface to figure out what we want to call y and z. After we do that, we won't have a choice. X will be determined for us. Once we pick functions to describe y and z, x is going to have to be 1 plus 2y minus z squared. So let me just try to draw a heuristic picture of this second surface. We don't really have to do this, but because x is a function of y and z, this is going to be some blob sitting in space, maybe like this, which cuts this cylinder in some vertical way. That curve of intersection that we get, who knows what it actually looks like, but heuristically it'll be something like that. And that orange curve is the thing that we're trying to parameterize. So the idea here is that if we were to look at just the equation y squared plus z squared equals 3, like we talked about earlier, that defines a circle in the yz plane, and we know how to parameterize circles. So this can be our starting point. In particular, I'll start out by just determining what I want to call y and z based on this blue equation. Y squared plus z squared equals 3 is a circle of radius square root of 3. So I could get a parameterization for that circle by calling, for example, y equals the square root of 3 times cosine of t, and z is the square root of 3 times sine of t. This is not the only thing you could do. You could certainly do other things, but it's one way to parameterize the circle given by this blue equation. Now, this curve is sitting in 3 dimensions, so we still need to pick an x component. But the idea is, now that we've decided what y and z are using this first equation, we don't have a choice. X, to lie on this intersection, it has to satisfy x equals 1 plus 2y minus z squared. We've called y and z something already, so we don't have a choice. X has to be this thing. So x has to be 1 plus 2 times y minus z squared is 3 sine squared t. And there you go. We can write this in vector form, and then we're done. We could call r of t x, y, z, where x is that mess that I just wrote down. Y is root 3 cosine t, and z is root 3 sine t. Done. Now, like I said, this is not the only correct answer. You could parameterize, for example, the y and z circle any way you want. The idea is that whatever you call y and z, x is a function of y and z. So the choices here determine the choice for x. This is a good general strategy to keep in mind for these problems, which is if you want to parameterize the intersection of two surfaces, oftentimes one of those surfaces will only involve two variables. Use that equation to determine those two variables, and then use the second surface equation to figure out your last component.